Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a very nice exponential equation with complex numbers. By the way, we did a different version of this problem before, and I'm planning to give you more versions as we go with the second power. And that was kind of like an easier solve because second power is easier than cubes, right? So in this case we have the third powers, which is gonna make it hopefully more interesting. By the way, if you came from CyberMath, say hi, because just yesterday we were talking about this channel, right? aplusbi, and I had a problem that was solved with complex numbers. Go ahead and check it out if you haven't checked it out yet. So we have this complex number, aplusbi, which is cubed, and then all of a sudden, mathematically, it turns into b plus ai. Okay? Great. So let's go ahead and solve this problem in two different ways. The first method, by the way, if you're new to complex numbers, go ahead and check out my lecture notes. And if you didn't know my other channel, my very first channel, it's called CyberMath, full of trigonometry, geometry, a little bit geometry, sorry about that, algebra and number theory problems. Go ahead and check it out. Let me know what you think. So our first method is basically going to be using like kind of brute forcey method. It is just expanding everything, okay? We have something cubed, so let's go ahead and expand it. So usually when I have something like x plus y cubed, I usually do it like this. X cubed, y cubed, and then I do 3xy, and then x plus y. The reason why I do that is because this is something that I also use with the cubic formula. It just comes from the binomial theorem, same thing, but it kind of makes it or keeps it a little bit more organized, okay? Because if you kind of bring that thing over to the left, I mean with an arrow, not a straight line, then you'll get the cubic formula, which is interesting. Now, but for this problem, we're not going to do it. So I want to replace x with a and y with bi. So here's what happens. A plus bi to the third power becomes a cubed plus b cubed I cubed plus 3abi multiplied by a plus bi. Now I cubed is I squared times I. By the way, I forgot to say, I'm assuming that you are familiar with complex numbers somehow. But I squared is -1, in case you didn't know. So this becomes -I. It gives us a cubed minus b cubed I. And then here, if you use the distributive property, you get 3a squared bi. And then here you get I squared again, so that gives you a minus sign, 3ab squared. Now this is a plus bi to the third power. Let's go ahead and rearrange the terms to make it a little simpler. I'm going to go ahead and put these two together. A cubed minus 3ab squared, that's the real part. And the imaginary part actually comes from here and here. So I'm going to write it like 3a squared b minus b cubed. That's going to be my imaginary part. Okay. Remember yesterday when we did the problem about systems of differential equations, we used a slightly different version. We didn't use x plus yi or a plus bi, but we used something like a plus ib. By the way, these two things are equal because they commute. Make sense? So it doesn't matter how you write it. Some people write it as a plus ib. No big deal. Now this is equal to the right-hand side, which is b plus ai. So we have like something very simple on the right-hand side, right? And left-hand side is more complicated. But what we need to do is also simple. Set the real parts equal to each other, and then of course automatically imaginary parts are going to be equal. So we get the following system. This, and then this equals this. How do you like this system? Let me know what you think. It's ugly, isn't it? Well, this is cubic, first of all, so it's probably hard to solve. But I'm going to do something interesting to make this problem kind of like more friendly, hopefully. We're going to go ahead and divide these equations. And then we're going to use cross multiplication, which makes sense, right? That's the whole purpose. So we're going to get a to the fourth minus 3ab cubed equals 3a squared b squared minus b to the fourth power. And then I'm going to put everything on the same side. It's going to look like this. A to the fourth minus 3ab cubed minus 3a squared b squared plus b to the fourth power. Now at this point, we're going to do something super Nice, super duper nice. And that's going to be to divide both sides by b to the fourth. And there's a good reason behind that. When you do it, this kind of turns, because it's homogeneous, it's going to turn into something nice. You can also do this. You can kind of set a over b to another variable like t, and then plug that in. It's pretty much going to do the same thing. So why don't we go with that? So we're going to replace a with bt from here. So that's going to give us b to the fourth, t to the fourth, minus 3bt multiplied by b cubed, minus 3b squared t squared, and then b squared again. So I probably need to move this out of the way like this. And then the last term is going to be b to the fourth, which is just b to the fourth, right? We just add that. Okay, great. So this is equal to 0. And notice that here we get 3b to the fourth t, and here we get 3b to the fourth t squared. So we can basically factor out tb to the fourth. Let's do that. And when we do, we get t to the fourth minus, from here we get minus 3t, and then minus 3t squared. I should probably switch them around, plus 1 equals 0. Now, do you want b to be 0? No, because if a over b is, you can't divide by 0. That's the point. And what happens if b is 0? Think about it. Well, if b is equal to 0, then we get a cubed equals ai, but a is real, so that's impossible. Does that make sense? So b cannot be 0. Since b can't be 0, this part has to be 0, right? That's the conclusion. So now we have the following equation. And that's what we need to solve. So how do you solve this equation? That's a good question, right? So here's what we're going to do. We're going to go ahead and, since it's quartic, we kind of need to write it in different ways. So we can eliminate t squared and then make the left-hand side a perfect square, even though we don't have to do it, but there's different ways to approach it. So let's go ahead and see how we can solve this quartic equation for t, and then that's going to give us the value of b over a over b, which we can use in one of these equations to find a and b, okay? We can go ahead and try the following. Suppose this can be factored into t squared plus at plus b. We don't necessarily know b is going to be 1 or negative 1. And then the other one is going to be t squared minus at plus c. Why did I assume a form like this? Because there's no t cubed in this equation. Actually, never mind. When I said we need to change this, we don't need to depress it. It's already a depressed quartic. So now we can go ahead and set them equal to each other. And from here, we're going to get a bunch of equations, like a system of equations. When you distribute, you're going to get t to the fourth power. And then t cubed is going to cancel out for sure. So you're going to get ct squared, if you distribute this, over that. And then with the at, it's going to cancel out, minus a squared t squared plus act. And then finally, you get bt squared minus abt plus bc. Let's go ahead and rearrange the terms, t to the fourth power. And then we have this, this, and this. So it's going to be like b plus c minus a squared. That's going to be the coefficient of t squared. And then we have ac minus ab as the coefficient of t. And then finally, we have the bc. And since this is equal to that, we can go ahead and set the exponents, coefficients equal to each other. This is supposed to be negative 4. This is supposed to be negative 4. And this is supposed to be 1. Now, b equals 1, c equals 1 does not work. b equals negative 1, c equals negative 1 does not work. As far as I know, I could be wrong, but let's go ahead and check that real quick. If bc is 1, that means, that's a good question. If b or c is 1, that's going to be real nice, but I doubt it. I don't think that's going to work. Well, suppose b and c are both 1, then we'll get something like this. 2 minus a squared is negative 3, but then we don't get a nice equation for it. Let's check it with the second one. If b and c are both 1, then this is just going to give us a 0. So yeah, you see, that's a good reason why they can't be equal, and they have to be equal if they're rational. Makes sense? Negative 1, or 1, 1. So it's impossible. So then we have to proceed with something else. From here, we kind of get a system, and I can show you how to solve it, even though it's kind of painful, because this is going to lead into a cubic equation. You can kind of factor out the a here, And then from here, you can replace c minus b with negative 3 over a. And then c plus b is equal to a squared. Go ahead and solve for b and c, treating c, the left-hand side as a system and a as a constant. You're going to be able to get b and c in terms of a, and then you can plug them into this one. But again, that's going to turn into a cubic. So there's another way to do it. Let's go ahead and talk about it. Maybe there's an easier way to solve the cubic, which I'm not seeing at this point. But let's go ahead and check out the second method, because I think the second method is really, really awesome. So, and this is something we used with the previous video too. So I want to set this equal to z as a complex number, and I want to know what would this be in terms of z, right? Well, here's the thing. To switch a and b, you kind of need to do a couple things. One of them is going to be the conjugation. The other one is probably multiply by I or negative I. Because when you multiply by, let's just take a plus bi, right? If you multiply by I, which is going to be iz, that's going to give you ai plus bi squared, which is minus b. In other words, negative b plus ai. You don't want that. You want b plus ai. So conjugation will do it, right? If you conjugate this, you're going to get b minus ai. But then you want the conjugate of that, right? So you negate and then conjugate. Does that make sense? So maybe we should do this. How about conjugate a plus bi, which is a minus bi, and then multiply by I. So it's going to be like this is z bar, this is iz bar, which is ai minus bi squared, which is going to be a plus b, which is b plus ai. There you go. So that is the transformation you need. In other words, if this is z, this is I times z bar. Z bar is the complex conjugate. So this equation turns into z cubed equals I times z bar, which is a lot easier than what we were trying to solve with the quartic, right? Don't you think? Now, obviously, you can go ahead and multiply both sides by z. That gives you z to the fourth power equals I times z bar times z. But you got to remember, z bar times z is absolute value of z squared. If you set absolute value equal to r, this gives you z to the fourth equals I times r squared. Interesting, right? Now, if you go ahead and do this interesting operation at this point, take the absolute value of both sides. Well, the absolute value of ir squared is just r squared because it's, what is it? You get the idea of the r squared is real. And this is going to be the absolute value of z to the fourth power, but this is r. So you're going to get something like this. R to the fourth equals r squared. Let's go ahead and simplify this. Factor out r squared. That's going to give you r squared minus 1 equals 0. From here, you get three solutions. R equals 0, r equals 1, and r equals negative 1. R is greater than or equal to 0. It can never be negative because it's the modulus, the absolute value. And if r is 0, then z is 0, which works because if you think about it, a plus bi to the third power, if this is 0, its third power is also 0, which can also be written as b plus ai, because in this case, a and b are both 0. Make sense? But that's a trivial solution. We're looking for the non-trivial solution, which is going to be given by r equals 1. And if you go back here, and in this equation, if you go back to z to the fourth equals I r squared, now we know that r is equal to 1. It's going to give you I. So we're dealing with the fourth root of I, because if z to the fourth equals I, then we're looking at fourth root. So let's go ahead and write this in polar form. So z to the fourth is going to be, I is e to the power I times pi over 2. But of course, you want to add 2 pi n. N is an integer, so you can get all the roots. From here, z is going to be e to the power I times pi over 2 plus 2 pi n all over 4. Make sense? So those are going to be the z values, but what are the z values? Let's go ahead and find some of them at least. For example, if n is equal to 0, z is going to be e to the power I pi over 8. And this can be written as cosine of pi over 8 plus I times sine pi over 8. How do you find those values? Well, you can use the double angle, half angle formulas, or if you want, you can find tangent pi over 8. I think in one of my videos on cyber math, I did make a video on how to find the tangent of pi over 8, and from there you can go to cosine sine. But I think the double angle for cosine and sine would be a lot easier to use. But they're going to involve a lot of radicals, and this will give you all the z values, which we weren't able to find by factoring because we didn't continue. But anyways, this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out Cyber Math, the Shorts channel, and this channel, which is A plus BI, and bye-bye.